So in the last video, what we got to at the end is that the general form for a tangent line is y equals the limit as h approaches 0 of f of a plus h minus f of a all over h. Where this is the slope, x minus a plus f of a. Well, I want to just simplify this a little bit. This whole green thing, that's the derivative at x equals a. So we could rewrite this as f prime of a. In other words, this is our derivative at a. So we could rewrite this as y equals f prime of a x minus a plus f of a. And again, this is our slope, this is x1, and this is y1. So we're going to use this idea. So let's say that we're given the function x cubed minus x. So we want to find the slope of the tangent line at x equals 1. Well, the slope of the tangent line, in other words, that's f prime of 1, the derivative at x equals 1. Two different ways of saying it. So how do we do that? Well, we know that, when x equals 1, f prime of 1 is going to, well, plugging that into a function, f prime, or just f of 1, rather, equals 0. And now we're going to choose a value of h that's really, really small. Because once again, we're going to use this idea, the limit as h approaches 0 of f of, well, let's do 1 plus h minus f of 1 all over h. So let's let h equal 0.1. So when h equals 0.1, so we're going to say let h equals 0.1, we're looking at when x equals 1.1, and we're going to find f of 1.1. Just so that we can start seeing this a little bit, let's pull up the graph. And let's graph our function so that we can see it. It may not, polynomials may not be clear immediately to everyone. So we're going to graph x cubed minus x. That's our function. And just so that we can see what it looks like. And let's press zoom 4 so that we can zoom in a little bit on it. And so what's very clear right away, when x equals 1, y equals 0. And now we want to find when x equals 1.1, what does y equal? Well, it equals 2.31. So let us take a picture of this, save it here. So what we need to do now is find the slope of the tangent line. Well, the tangent line, in order to do that, we're letting h be 0.1, a small value of h. So we get these following points. We get the point, doing the work over here. We get the point when x is 1, y is 0. So have to see there. And then we get the point 1.1, comma 0.231. And that's the point that we just found down there. So our slope, which is the slope of the tangent line of the instantaneous rate of change, or the derivative at x equals 1, or f prime of 1, all meaning the same thing. Our slope is 0.231 minus 0 over 1.1 minus 1, which equals 2.31. This is my instantaneous rate of change So I found the instantaneous rate of change, which is the same thing as the slope of the tangent line. So now the equation for the tangent line is going to be y equals the slope, 2.31 times x minus, well, x minus 1. We're looking at x equals 1. And then the y value is 0, plus 0. So now if I were to sketch this graph, if I were to put this graph of the tangent line on top of my function, what I'm going to get is a shared point at 1, 0, and the tangent line is going to be approximating the curve in that small area. So, in other words, if I were to get my graph out and also graph 2.31 x minus 1 and graph it, we see that when x equals 1, the tangent line is doing a very good job of approximating the curve. Let's keep thinking about derivatives. And what we did a couple days ago is we found derivatives by zooming in on a calculator and waiting until a function became linear. So let's look at this new function, y equals x squared minus 1, the absolute value of. So we're going to go the absolute value of x squared minus 1. And we're going to graph this. And it says find f prime of 1 and f prime of 2. Well, f prime, remember, f prime of 1 or f prime of 2, this is just saying find the derivative or the instantaneous rate of change or the slope. You know, this is the slope of the tangent line at x equals 1, or the slope of tangent line at x equals 2. That's a way to think about it in terms of a tangent line, or you can think of this as the derivatives at x equals 1 and x equals 2. Okay, so we need to do some zooming. So if I want to zoom in at x equals 1, then I zoom in there. So if I zoom in at the value of x equals 1, and I'm going to zoom in, and it might be even better to do zoom box. Oops. Okay, so I started that again. So zoom box, we need to press enter and make a box around x equals 1. And I zoom in, and I'm not getting a line yet, so let's press zoom box again. So zooming in again around x equals 1. Zoom box. And what we notice is that as we zoom in and zoom in and zoom in here, as we keep zooming in, no matter what, this area right around here does not become linear. And this brings up an important point. The there are going to be some functions at some points where we cannot get a line. So in other words, here's the point, x equals 1 right here. And no matter how much we zoom in on this area, as we zoom in, it never becomes a line. And if that's true, if it never becomes a line, then it has no derivative. And we'll talk a lot more about this in the next couple of days, but just graphically, because we're asking you to solve derivatives by graphing, if you do some zooming and you get no straight line, there's no derivative. The converse being, let's zoom in on, let's find f prime of 2, or let's look at the derivative when x equals 2. And this is going to be very different. When x equals 2, if we zoom out again, so let's go zoom 6, and let's zoom in, let's do a zoom box rather, at x equals 2. Okay, for some reason my zoom box is not working, so the other way of doing this is getting the value of x equals 2, and then we're going to zoom in there. So press zoom in, and we zoom in, and let's do that again. So second calc, let's get the value when x equals 2. So there we are, and then we're going to zoom in again on that. And now we've got a straight line. And what we can do is we can choose this point that's on the graph, if we trace it. So now we've got a point on the graph. Let's take a picture of that. So we've got this point that's on the graph, and we know that the other point is when x equals 2. So we know when x equals 2, my function, when x equals 2, my function is going to be 3 by plugging 2 into here. So when x equals 2, y equals 3, and I've got this other point here. So I could find, because this is a straight line, because now we have a straight line as opposed to here, where there was no straight line. It never becomes a line. Here we get to a line. So therefore we can talk about the slope, so the derivative of x equals 2. And that's going to equal, doing some rounding, 3.09 minus 3 over 2.02 minus 2. And if we simplify this, we get 4.5. Or in other words, the slope of this line, slope equals 4.5. And we did that by zooming in on the graph until we got a straight line. Once we got a straight line, we took one point from tracing, and then the other point just from looking at a point when x equals 2 and evaluating the function. And with these 2 points, we were just finding the slope, because the derivative is just the slope. All right, so the last example that we're going to talk about, finding the derivative at x equals 0 of this function f of x equals sin x, and we're going to do this on a new video so that it